Hey guys, welcome back. Now let's go ahead and understand depth first search traversal. So in this traversal, we start with a vertex, we visit this vertex, and now from here we select one of its branches to read all the vertices that come in that branch. And then we move to the next branch. So in this traversal, we go branch by branch until all the vertices are covered. For example, see here, if we start with from 1 and we pick one of its branches, which we do by selecting one of its adjacent vertices, which is, let's take 2 here, and then we repeat the process. We came at 2, now we have to select one of its branch. So we select 5 and then we again do this. So in this manner we complete one branch, and after completing the branch there is no further recursion. We go back to the previous call and we see if there are more branches. If there is any, we pick that and we try to complete that. So this goes on until all the vertices are covered. But what you are seeing here is an acyclic graph, which is actually a tree where we don't have cycles. So we don't visit any node more than once. So the catch with graphs is graph contains cycles. Consider this graph. We start traversing this node, then we pick a branch and traverse all the nodes in this branch. We go to 2, then 4, then 7. From 7 we again go to 2, but this vertex is already visited, right? Hence, to avoid visiting node more than once, we need to keep track of all the visited nodes. And for that, we take a data structure, let's call it visited. So visited will store a Boolean value corresponding to each vertex. If the vertex is already visited, the Boolean value for that vertex will be true. So here 1, 2, 4, and 7 are already visited. So these will be having true as their respective value. Now see in this graph, from 7 we don't have any node to go further. At this point, execution gets back to the node from where it came to the current node. So we came to 7 from 4, right? So execution get back to 4 and then it check if it has other branches to traverse. No, 4 is not having any branch. So again, the execution gets back to the previous node, which is 2. So it gets back to 2 and look for the branches. It finds 10, again gets back to 2, and then move to the next branch. So this goes on. So that's how DFS traversal works. This is recursive in nature, so we usually implement it using recursion, but we can also do it using iteration. Let's see how we can do this using recursion. We pick a node, let's call it source. So we visit this node, we mark it as visited in the visited array or visited list, and at the same time we print this node. Then from here we reach out to the adjacent nodes to this S one by one inside a loop, and we see if the node is not already visited, then we recursively visit it. So when all the nodes gets visited in a branch, the execution gets back to the node in the same path to traverse rest of its adjacent nodes recursively. So that's the recursive approach or recursive implementation of DFS. Now let's see the iterative approach. We pick a starting node and we push it into the stack. Then we pop it and visit it. And to show that, we print it. Now we iterate over its adjacent vertices to pick them one after the other to be pushed next into the stack if they're not visited yet, so that these branches gets visited next. This goes on inside a while loop for all the vertices. Each time a vertex gets popped out of the stack, its adjacent vertices that are not yet visited gets pushed into the stack. So here we are using stack because of its first in first out property. Here each time only the topmost vertex is going to get popped out of the stack, and at each elimination the adjacent vertices to the eliminated vertex are going to get placed at the top of the stack. So this way one branch gets traversed completely and then the execution is able to get to the next branch. So this goes on until there is any node present in the stack. So this is how the iterative approach works.